So that way we can I know we're all on the same page. So I apply this force of 0.98 newtons until we get to here, until it goes 0.75 meters on a friction-free surface. Then once you get to this friction surface, I'm no longer applying a force. The book slides for 0.5 meters, and then it is done moving. Does that make sense? Yes. Okay. So what is the work done by me over that first region? What'd you get?
188.
Okay, how'd you get that, Maria?
73.5.
73.5?
No, 0.73.
0.73?
Ah, yeah.
Okay, so how'd you get that? That's all right. How'd you get that?
The 9.98.
And?
9.3.
Perfect. So the work done by me is the force 0.98 times the displacement of 0.75, right?
Yeah.
Oops, that's equals. And we get point what? 73?
Yep, 73.
Okay. 0.73 joules. Does that make sense, guys?
Yes.
Okay. That's an easy one because the force and the displacement, right? Here's our displacement. The force and the displacement are in the same direction. Good. Now, what is the work done by the normal force? Which way is the normal force point? Up. So our force normal is like this. Displacement's like that, right? What's the angle that those two make? 90-degree angle. They're perpendicular. Good. So what's the force done? Some people are probably thinking, I don't know the mass of the book. How can I figure this out?
0.
Okay. Well, work equals force times distance times the cosine of theta, right? Right? What's theta in this case? 90. Those you have to memorize your unit circle. What's the cosine of 90? Equals 0, right? Type in your calculator. Cosine 90. It's a good way to check to see if you're in degrees or radians. If you're in degrees, like you should be, you get 0. Right? 0 times anything is 0. Okay? So, when the book gets to here, how much energy does it have? 0.73 joules, right? The book has 0.73 joules of energy at this point, right? What type of energy is that? Kinetic, because the book is moving. So the kinetic energy at that point is 0.73 joules. Does that make sense, guys?
Yes.
Okay. Now the book slides for 0.5 meters. And what happens?
Stop.
It stops. So what's our kinetic energy equal to here? 0. Did all that energy turn into potential? No, because we didn't change our height, did we?
No.
So no potential energy is added. So what happened to that energy? Sergio, wake up. What happened to that energy? It was used. If it's used, that means we can't get it back, right? So is it destroyed? It's transferred. What transferred it? I didn't transfer anything. What transferred it? Friction. Right? How'd friction transfer it? But I thought forces and displacements do work, right? Doesn't work increase energy? Doesn't work increase energy? Alright. Does work always have to increase energy? No. In this case, what is the work done by friction doing? Slowing it down. The work done by friction is taking energy away. Right? So I didn't give you the force of friction intentionally. Right? Because how much energy do we have right here? How much do we have right here? 0. So what happened to that energy? was taken by friction. So what is the work done by friction? You're close. 0.73 joules, right? But it has to be negative. Okay. Friction takes this energy away. All right, does that make sense? So why does friction take that energy away?
It doesn't keep going forever.
No, but why does friction take it away? Because it wanted to. Okay. Because if the book's sliding this way, which way does the friction force act?
Opposite.
Opposite way. Friction's going this way. Right? Friction opposes motion, doesn't it?
Want everything to stop.
Right? Friction opposes motion. Which way is our displacement? Which way is the displacement? That way, right? So what's the angle between friction and displacement? I'll draw right here. So here's the force of friction. Here's the displacement.
Oh, 180. Yeah.
What's this angle? 180 degrees, right? So far to this point, we've talked about if force and displacement are in opposite directions, then the work is negative, right? Are these two in opposite directions?
Yes.
Are these two in opposite directions?
Yes.
Okay. Now the reason why that work is negative is because it takes energy away. Okay. Now, how this works with equation 4 is I need to look at the cosine of 180, because equation 4 says work equals force times displacement times the cosine of 180, right? Right? Does anybody know the cosine of 180? -1. So anytime our force and our displacement make a 180 degree angle, meaning they point in opposite directions, right? Then our work will be negative. Does that make sense? Okay. Now, if I am using this 180 degree angle, we do not think of force and displacement as vectors. We just use their magnitudes. Okay. The other way I can look at this is by saying these two are opposite directions, so one has to be negative. Then I don't need the angle. Does that make sense, guys? You guys see what I'm saying? So I could say these two are opposite directions, so one's negative. Then I don't need to do cosine 180. If I do cosine 180, I don't need to make one of these negative. Okay? Does that make sense, guys? All right. So the work done by friction is negative 0.73 joules because it takes away all the energy the book had. Stops it. All right. Does that make sense, guys? Okay. Now, could we figure out the force of friction acting on the book? Probably. Right? We know work is negative that, right? What's the displacement? What's the displacement? 0.5, right? What's the force? Don't know. What's the angle? 180 degrees. So, work equals FD cosine theta. Can we find F? Can we find F? Yeah. You have negative 0.73 F times 0.5 times cosine 180. You guys solve for F? $1.46. How'd you get that, Richard? Algebra. Hoping you would elaborate on that. Cosine 180 is -1, right? So we simplify the right side, we get negative 0.5. Divide by negative 0.5. And we get force equals 1.46 newtons. Does that make sense, guys? Yes, Kim.
When they're always going in the opposite direction, you always want to use cosine 180.
You can. You have two choices here. You can say the angle between friction and displacement. As friction goes this way, displacement goes that way. You can say the angle is 180 and do it this way. Or you can say they're going in the opposite directions, so one of them has to be negative, and then just tack a negative sign onto this equation. Okay. So you either use this one or you use 180, right, without direction, or you pick a direction here. Pick one as positive, one as negative.
So for the W, you don't need cosine in there?
You don't need cosine there. You can just use the magnitude of the forces, and then make one negative. Okay. Richard.
Do we use that W which is FP equation for every one that has an angle?
This one? Yes.
So we substitute it for that every time?
Anytime you have an angle, you can use this one.
No, I mean the top.
The top one? If you want to use this one all the time, then you need to break F and D into components before you bring them into this equation. Okay? What this one does is this finds the amount of force and distance that are parallel to each other. Okay? So anytime they're at an angle, I'd use this one. Alright? Don't worry about directions of F and D, but plug in the angle. Alright? That's what your homework was about. Okay? Any other questions? Alright, so here I have a block being pushed by forces in different directions here. The displacement vector is shown. Alright? I want you to think about what kind of work each of these will do. Alright, your choices are positive work, negative work, and zero work. Okay, I don't want you to shout it out, alright? I just want you to take a look. Alright, so I'll write that up here. So your choices are positive work, negative work, or no work. What? Nope, you're just looking at the forces that I have drawn here, force and displacement I have on here. So, the question is, does the force do positive work, negative work, or zero work? Okay. Does this force do positive work, negative work, or zero work? Positive work. Does this force do positive work, negative work, or zero work?
Zero.
Zero work. Positive work, negative work, or zero work? Negative work. Why is it negative?
Yeah.
Because the force and displacement are in opposite directions. Okay, does that make sense? Okay. So, let's say I fill my backpack up with my 3 books. Okay? Got my math book, I got my physics book, and those are little books.
No.
They're big books? Okay, my language arts book. My dictionary. Alright.
2 of them.
So, 2 of them. Wow. So, my backpack's got 3 books in it, my folders and everything, and I'm walking around on the first floor. And man, my shoulders are killing me. Alright? Did I do any work on my backpack? Did I do any work? No. I did no work. Right? Because which force do I apply to my backpack? I apply an upward force to my backpack, don't I? For my shoulders? Which way has my displacement been? Side to side, right? As I walk around, my displacement side to side, my force is up. Did I do any work? No, I did no work on my backpack. Now when I lift it off the ground and put it on my shoulders, I did a little bit of work. Right? Not until we climb up the stairs do we actually do work. Because then our force and our displacement are in the same direction. Does that make sense? Kind of like when if you're helping a buddy move. You got a big handful of boxes, right? It's so heavy you're carrying it, but you're not moving up or down. Okay? You're not doing any work. No work is being done. Okay? Once you step up step, though, then work's being done. Does that make sense? Kind of makes you upset, though, doesn't it? Because your muscles get all fatigued, don't they? Right? Your muscles are still applying a force, and they're fighting gravity, so they can still get fatigued. All right? All right, any questions about work, positive work or negative work or no work? Any questions?